Hello and welcome to this lecture on in the chemical process modeling and simulation series. This lecture is a set of the initiation of a set of lectures on distributed parameter systems modeling, and we will be looking at a set of case studies. First one involving heating and cooling problems, and in that the first particular focus is going to be on double pipe heat exchanger, and there will be two parts to this lecture on double pipe heat exchanger. To sort of quickly recap, what are distributed parameter systems? These are systems where the independent variables or the parameters in the system vary along the position at different locations. There are different values for the parameters. For example, if you consider flow through a pipe, right? The velocity is a radial function of radial position. Now, if there is a plug flow, then the velocity is no longer a function of radial position. Nonetheless, at least the pressure is a function of axial position. Now, if there is heat transfer happening alongside, just as it would in a double pipe heat exchanger, then temperature is also a function of axial position. Now, if there is additional mass transport, species transport, reactions probably happening along the length of the pipe, like it would in a plug flow reactor, then concentration of the species or conversion of the species is a function of axial position. So this kind of models are distributed parameter models, and we are going to look in the first part at a one-dimensional model where we assume that there are no axial variations. There are no radial variations. There is only axial variation, and this basically is the quote-unquote assumption of plug flow, right? So we are going to look at that, and then in the second part of the lecture we will relax this assumption and then assume a very specific scenario where there is a laminar flow of the fluid, and but that the momentum transport equations can be uncoupled and decoupled from the energy transport equations. And we will even discuss under what conditions such an approximation is legitimate, but we will consider that model of a double pipe heat exchanger. So in the first part we are going to have a distributed parameter system that is in one dimension. In the second part we will consider in the double pipe heat exchanger itself a distributed parameter model of the double pipe heat exchanger in two dimensions. So one could of course also account for third variable, relaxing the symmetry in the third variable, which would be the theta variable, and this would occur when there is mixing, when there is turbulence, for example, but not so much of turbulence that there is one could approximate the flow as a plug flow, right? So in such scenarios, then one could have a three-dimensional distributed parameter model. And this is spatial dimensions that we are talking about. Of course, there can always be a temporal time variation also. Right? So with this background on double distributed parameter systems, we move on into double pipe heat exchanger. So heating a flowing liquid or a flowing fluid is a very common problem in chemical engineering. Right? It's a common problem, and this is accomplished using various designs of what are called heat exchangers, where mostly one fluid is heated by bringing it in indirect contact, not oftentimes direct contact, very rarely direct contact, but usually indirect contact with a separate fluid. So if you have to heat a cold fluid, then it is brought in indirect contact with a hot fluid, and vice versa. Right? So how is this indirect contact facilitated? By making sure that these two fluids don't mix with each other. So geometrically they are separated. There is one pipe through which one fluid flows, another pipe through which another fluid flows, or a series of pipes through which one fluid flows, and then there is the annular region in which all these pipes are enclosed, through which the other fluid flows. So there is a geometric separation by way of typically some sort of a solid boundary, right? So therefore, heat exchange problem oftentimes becomes a problem involving at least three phases. So there is one hot fluid, there is one solid, there is one cold fluid. The solid is the boundary that separates the hot fluid from the cold fluid. So at least three phases will have to be considered in a heat exchange problem. And this is assuming that there is no phase change in either of the fluids. So the simplest model would be a model where one does not have to consider phase change, and if one considers phase change also, then one does not consider alongside the phase change sensible heating or cooling, and one does not consider momentum transport. There is no reaction, there is no you know uh, basically diffusive species transport of any kind. Then all those other mechanisms are eliminated, then this becomes a simple pure heat transfer problem. And this is the first model that we start looking at. So if you consider a double pipe heat exchanger, and then we consider, for example, saturated steam, considering in the outer side, in the annular region, outside the inner pipe. So then basically the temperature on the outer side remains constant. So we are only looking at latent heat that is being lost through the inner pipe wall to a colder fluid which is being heated as it flows through the inner pipe. So now, if the flow of the inner pipe, then inner pipe fluid, cold fluid, if that flow could be considered to be a plug flow, then there is no momentum transport, and also if there is then there is momentum transport is, equations need not be considered. Basically the velocity is taken to be fixed, and if there is no phase change, the cold fluid doesn't vaporize or condense or whatever, so basically that means there is only sensible heating, and a pure heat transfer problem, simple heat transfer problem results. So this is a typical picture of a double pipe heat exchanger. The inner pipe is seen through the bends, and then there is an outer annular region, right? And there is an inlet here, and there is a second inlet here. Similarly, there is an exit here, and there is a second exit there. Okay, so or vice versa, one could be the inlet, but could be the exit, depending on the flow patterns that you choose. So there are two flow arrangements that one can then consider. Basically, one of course is a counter flow, the other is a parallel or co-current flow. Counter current and co-current, or counter flow and parallel flow. In a counter flow, the cold fluid and the hot fluid end up flowing in opposite directions to each other, whereas in a parallel flow, both flow along the same direction, parallel to each other. So these are the two flow arrangements. So notice that this means the end conditions for the fluids are different, or what are different. So anywhere in between the inlets and the exit, okay, so at any point, any cross section, any distance from the inlet to the exit, defined inlet being defined from the left end, and then exit being defined at the right end. So for the sake of convention at this point, right? So at any distance from the left inlet, right? So if this were denoted as the z-axis or the axis of flow, right? Both a cold fluid and the hot fluid would flow in along the direction of plus z in a parallel flow, whereas here if you look at it, the cold fluid will flow in the direction of plus z, and the hot fluid will be flowing in the direction minus z, right? So that's the difference. But at any cross section z, now if you z equal to whatever value, right? So if you look at the equation, that shouldn't be different at all for a counter flow versus a parallel flow, because here there is the hot fluid is at a certain temperature, cold fluid is at a certain temperature. The wall, the inner pipe solid face is at a certain temperature, or at over a range of temperatures basically. So there is heat transfer that is occurring. So that's all that one needs to look at, one needs to bother, right? So this is the sort of picture that the equations that we derive for the temperature variation along the length of the heat exchanger would be valid for both counter flow as well as parallel flow. It is only the end conditions that would be different for these two flows. Now, in the previous lectures, we developed conservation equation for energy, conservation equation for momentum, conservation equation for mass and species in vector tensor notation. Now, those equations could be taken in this particular case, energy equation could be taken, and they may be used to reduce simplify to the form that we are going to see at the end of this derivation. However, to give another flavor, another approach for performing energy balances, so we are going to consider shell energy balances in this particular model development. So here is a picture taken from rice and dough. So here there is this is a small shell, thin small shell with very small thickness. The shell is between z, z and z plus delta z, z plus delta z with a thickness delta z, and this is an arbitrary infinitesimal thickness. So this is your cross section. The inner pipe has a radius r, the cross sectional area is a, and then the temperature of the fluid entering this section is T of Z. The temperature of the fluid exiting the other sections, Z plus delta Z, is T of Z plus delta Z. And this is basically the wall, solid wall. And one could imagine there is another basically cross section that basically encompasses both the inner pipe as well as the wall, and then outside that would be the outer fluid, the hot fluid, right? So what we are going to do in developing this model is we are going to consider only variation along this one dimension, the axial dimension, which means we really do not account for a radial variation of any parameter. So temperature is constant at any cross section, which means the entire contents of this cross section are so perfectly mixed that everywhere from the wall to the center, the temperature is uniform, right? So basically that is the idea, and the momentum is also uniform, and therefore the fluid has a constant velocity everywhere in this cross section, which we know from our momentum transport discussions is not exactly correct. So there should be a velocity profile because there is friction here which should result in no slip, and then here there is minimal friction and there should be maximum velocity therefore, right? However, some variation, I mean, even if one does not consider laminar flow, there is turbulence and therefore there is mixing of momentum between fluids of different layers. This is another idealization, extreme idealization, that there is a perfect mixing to so as to result in a constant velocity v. Now, therefore, since we don't allow for any radial variation, we also don't allow for any, or we don't consider any variation along the thickness of this wall, and so the wall temperature is practically the same as the other there is the hot fluid temperature, if you are interested in, or from the hot fluid perspective it is the same as the cold fluid temperature that if you're interested in. So in effect what we are saying is that the thickness of the wall itself is so small compared to the radius that it is negligible. So we are just going to consider one cold fluid temperature and then one hot fluid temperature, and that's it. We are not going to bother about defining any temperatures in between of the wall. All right. So with these severe assumptions, actually, let us try and write the model equations. And the idea is, even when we make such seemingly unreasonable assumptions, the idea is to develop a model as an exercise first to show to the students, to the people who are listening to this lecture, um, how a mathematical model may be used to analyze the system behavior, the behavior of a double pipe heat exchanger, and what is the controlling physics in the behavior of the double pipe heat exchanger, and how to identify it. So it's more like a tool, sort as an example. It is being illustrative, and therefore things are kept reasonably simple. Okay, so with that background, then we perform an energy balance. So we should look at the rate at which energy is entering this shell, rate at which energy is leaving this shell from here, and rate at which energy is added to the fluid in this shell. Now, so we are going to write those equations, those terms here. Now, this is the rate at which the energy is convected into the shell. This is through bulk flow, right? And this is basically rho AV, so that is mass flow rate, times Cp, which is basically now this is the whole thing. At any cross section there is a constant pressure, and therefore there is a pressure difference that drives the flow. So the specific heat capacity is evaluated at constant pressure, and then this T is the temperature of the cold fluid, and all these C subscripts indicate cold fluid, whereas the subscript H indicates hot fluid. Now, of course, there has to be Tc minus some reference temperature. But that reference temperature is not considered, because here also that will be there and it will get cancelled. And for these also they will be there, they will get cancelled. And when you take the derivative with respect to time, then also the reference temperature will get cancelled, and therefore that is not considered, right? So the first two terms therefore indicate the energy. The first two terms therefore indicate the energy convected by the flowing fluid at the inlet and the exit. The difference is basically what should be the energy added by the hot fluid and the accumulation. I believe there was a small pause during this time at some point. I apologize for the same. Some issues with the computer. So, given that this is the case, now the energy added. Now, I want to spend just a moment discussing the energy added. So, this is basically U A delta T. So, this is the heat transfer coefficient. That is the area through which the heat is added, and that is the difference in temperature. That is the driving force for this heat transfer due to what is typically called advection. So there is both conduction from the surface and conduction across the interface. I hope it is understood clearly that for pure convection to take place, there has to be a bulk flow, and from the solid surface to the fluid at this interface, at this circumference, essentially the perimeter, right? So here there is no bulk flow of any kind, and therefore the mechanism by which energy can be picked up from the wall boundary by the fluid is exclusively conduction, exclusively molecular energy transport. However, one cannot define a heat flux across this boundary, because thermal conductivity is a discontinuous parameter, and therefore Fourier's law of conduction it cannot be written. So for such interface, heat transfers across multiple phases, therefore one has to write a different expression for the heat flux. Besides, this fluid is not a stationary fluid. This fluid is a flowing fluid, and therefore in this particular scenario, when the inner fluid, pipe fluid, is flowing, the velocity or the momentum of the inner pipe fluid, which is the cold fluid in this case, is going to in turn influence the extent of heat being transferred, and therefore this heat transfer coefficient will turn out to be a function of velocity. And this is oftentimes in your heat transfer courses, you would have studied this as correlations between Nusselt number, which would be proportional to the heat transfer coefficient, and Reynolds number, which would be proportional to the velocity of the flowing fluid. Right. So therefore this Newton's law of cooling is written as a constitutive relation to capture this complex multi-phase heat transfer process going from one solid phase to another fluid phase, heat going, or vice versa, heat being transferred, thermal energy being transferred in the form of heat, right? Energy in transit. So therefore now this therefore has to be energy transferred at only the boundary, right? And therefore shouldn't this term, the Newton's law of cooling, appear only at an end condition? How does it appear in the bulk, in the equation, the energy balance equation? Now if you ask yourself, this energy is transferred into the fluid at the radius equal to capital Ri, the subscript I indicating that this is the radius of the inner pipe, right? So this flux will be the heat flux, and this flux of course is equal to the minus k dTcd dr, the radial temperature gradient, if you would go from the wall to the center of the fluid, right, center of the inner pipe, right? So the temperature gradient, radial temperature gradient measured at that boundary times the thermal conductivity with, of course, the minus sign, that should be the heat flux. That is the rate at which heat is picked up by the fluid at in contact with the solid boundary, right? And so one should actually write this as a condition that this heat flux is basically valid. It is written at the boundary R is equal to capital R. In fact, this is what we would do in the next part of the lecture when we consider two-dimensional distributed parameter model. However, now since we don't have any radial variation at all right, so there is no meaning for any parameter temperature variation at R is equal to capital R versus R is equal to 0. Everywhere the temperature is the same, and therefore this heat is transferred as if from the hot fluid directly into this cold fluid, the entire cold fluid in this cross section, right? And therefore such set of such cross sections going from Z to Z plus delta Z is given by this 2 pi r, which is basically the circumference, times the thickness, which is the delta Z, and through each of such cross section you would have this heat transferred, and that is why this energy is added into the bulk fluid itself, right? So this is this term, and the last term is basically this is pi r square delta Z is the volume, and then multiplied by the density gives the mass, times specific heat, times again Tc minus the reference, some reference temperature. And then when you are looking at time variation, accumulation or depletion, so that gives rise to this partial derivative. Now in writing this the accumulation term in this fashion, what are the assumptions we have made? We have made the assumption that the density does not change with time, the specific heat capacity does not change with time, right? And these are basically the assumptions that are made. They are taken to be constants. So this is the shell energy balance. Now, if before we proceed further, so of course the assumptions that are discussed are plug flow, constant velocity of the cold fluid, purely thermal modulus required, the energy balance is this equation once again. So before we proceed further, I want to sort of just briefly touch upon how would such an equation result in from the conservation of energy standpoint. But before doing so, I would like to divide throughout by pi r square delta z rho c c p c, which is this term, and then we take the limit of delta z tending to 0, so we end up getting this equation. Now this equation has some familiar features compared to the energy conservation equation that we have seen. This is the accumulation term, this is the convective energy flux term, and this of course is Newton's law of cooling, which replaces basically your del dot q kind of term that one would write the conductive heat flux or radiative heat flux or whatever it is. But this comes basically, this should actually be 0, all right, and this should not show up at all, except because we don't have radial variation in temperature, and therefore this doesn't show up as a boundary condition at r is equal to capital R. Now there are two conditions, initial conditions that are needed, one in time and one in position, to get the particular solutions for this differential equation. This is by the way first order partial differential equation in both time and position. And if one were to consider this kind of similar kind of equations, one would see in inviscid, that is if one were to neglect friction and neglect even gravitational effects, for example, and one were to consider the compressible fluid flow of air, so I am speaking now, you are listening to this this lecture, and the air is vibrated through compression and rarefaction by the speaker phones of your device through which you are listening to it, and then the air travels, that wave travels and hits your tympanum, which in turn is translated into what you are hearing. So that sort of compressible flow in terms of fluid compression, expansion, those waves are modeled by such equations. And similar such waves as in blasts, explosions, in earthquakes, tsunamis, could all will have the fundamental, this structure is going to play an important role on the left hand side. Of course, this is temperature thermal model, and that we are talking about there, it is something else entirely. It's momentum transport and density change and whatnot, right? So that's a different quantity that is conserved, but the equation structure is similar. Now coming to these initial conditions, so the first one is for all times, even after you have started operating the double pipe heat exchanger, at the inlet Z equal to 0, the cold fluid has a temperature Tc in, which basically says if one were to go along the axis from left to right, this the left end being Z equal to 0 and the right end being Z is equal to L. Basically what this second condition tells you is that at Z equal to 0 at the left entrance, always the inlet temperature is Tc in. Now the other one, T equal to 0 for all Z, this sort of gives the initial startup condition, so to speak. So this sort of says how are you starting up your double pipe heat exchanger. So of course this is hypothetical at some level, you have to approximate somewhere. So initially the idea that is being talked about is that everywhere along the inner pipe for all Z, so at time T equal to 0, the cold fluid is filled already before heat transfer process starts, and then that is, so initially the cold fluid is at the same temperature as whatever the inlet temperature is. Okay, so similar expression will be written for hot fluid also. But for the time being, we are looking at, of course, saturated steam being condensed, and so somehow the idea is that at time T equal to 0 or less than 0 or whatever it is, at least at time T equal to 0 at all Z, Tc is Tc in, and Th is the hot fluid temperature, which is basically the saturation condensation temperature of steam, at that pressure, whatever the system pressure is. All right, we assume that the annular pressure, the pressure drop is negligible and the change in temperature is negligible. So it's some constant value. Okay, so at t equal to 0, this th is some ts. All right, and tc is tc in everywhere, but somehow heat transfer has not started until that point. So so there is some approximation involved in that. Right. So this is the model for double pipe heat exchanger, the inner pipe for the cold fluid temperature, purely thermal model, assuming that the velocity need not be solved from the momentum transport equation. We are going to take this to be constant and take it out. Now we move on to a very important part of this modeling exercise. We are going to perform what is called a scaling analysis, and we're going to define dimensionless variables based on characteristic quantities in the system. My approach for this is going to be, initially I'm going to give a whole set of examples: distributed parameter systems, lumped parameter systems, stage parameter systems, and so on and so forth. So where we will just define these dimensionless variables, and then eventually at the end I hope to generalize the approach that we are taking and sort of observe what are the common features, how to go about for an unknown model, for a very complex model, for example, how to define characteristic quantities, how to define dimensionless groups, and so on and so forth. So those sort of more abstract ideas will be taken up after there are sufficient examples that we've all been exposed to. So we start by defining the dimensionless variables to start with. There are two independent variables. One is a position, axial position z, and the other is time. So to define a dimensionless variable in z, there is a characteristic length that is chosen along the axial direction, which basically is the length of the inner pipe where the heat transfer takes place. So that length is L. Okay, and then so a dimensionless variable is defined y, which is z by L. So y varies from 0 to 1, whereas z varies from 0 to L. Now we come to time. So if you look at this double pipe heat exchanger system, even in the equation that we developed, it is ideally apparent that there are two phenomena that are taking place. One is bulk convective transport of the cold fluid through the inner pipe, which is captured by the left hand side of the equation, and the second is the heat transfer into that flowing cold fluid from the hot fluid through the mixed conduction, convection, advection, Newton's law of cooling. So that is the heat transfer. So each of these phenomena will have a characteristic time constant associated with it, characteristic rate associated with it, characteristic velocity associated with it, characteristic flux associated with it. One could write so many of these quantities for each phenomenon, oftentimes competing with each other, that together in some combination determine the behavior of the overall system, in which case here is the double pipe heat exchanger, and particularly the heating of the cold fluid in the double pipe heat exchanger, right? So that's what the model equation is for, right? So the entire question of how much heat is that the cold fluid going to be heated is answered by understanding how these two competing phenomena combine with each other. What are the competing phenomena? Again, flow, axial flow along the z direction, and in the dimensionless coordinate system along the y direction, and the heat transfer from the hot fluid to the cold fluid, right? In ideally what should be thought of as the radial direction, but that we are not looking at a radial variation, and therefore the heat is just added at every cross section as we go along uniformly. Everywhere in the cross section, the same amount of heat is added, right? So basically that's the heat transfer. So for these two phenomena, one could define characteristic times. So since we are trying to define a dimensionless time, we have to choose one of those characteristic times as a time with respect to which we are going to define a dimensionless time. Just as we take the characteristic length along the radial direction and say 0, 0.1 L, 0.2 L, 0.3 L, 0.4 L up to L. So similarly, we have to look at characteristic times. So suppose this characteristic time is indicated by an uppercase t. So then you say lowercase t is varying from 0, 1t, 2t, 3t, 4t. So it's in units of this characteristic time we are going to sort of express it, instead of expressing the time in absolute units, 1 second, 2 seconds, 3 seconds, and so on and so forth. So we have chosen here the characteristic time associated with the bulk flow. Okay. So there is a logic behind this, which shall be discussed when we look at the overall process, the generalization of how this whole dimensionalization or rendering the model dimensionless is attempted, right? But for the time being, choosing the phenomenon of bulk flow of the fluid as the sort of characteristic phenomenon, then what we have done is we have defined the characteristic time associated with it. Now, the characteristic time is typically defined as characteristic length by characteristic velocity. Length by velocity will give a time. Volume by volumetric flow rate will give a time, right? So there are ways to obtain time, right? So we have taken this characteristic length for the axial flow, which is of course L, and then the characteristic velocity for the axial flow is constant here. It is the plug flow velocity Vc. So L by Vc will give a time, and then T, which is the real time in terms of absolute units, 1 second, 2 seconds, 3 seconds, and so on and so forth. When you take that T and divide by the characteristic time L by Vc, you get a quantity which is a dimensionless time. So that is indicated by the symbol tau. L by Vc, by the way, is it could be called T bar. For example, it is the mean residence time for this plug flow. And if it is an ideal plug flow, then there is only one value for that. I mean, there is no distribution of that residence time. If it is not an ideal plug flow, then there will be a distribution of the residence times. And this you may have studied in your chemical reaction engineering course, right? So then comes the dependent variables, which are basically the two temperatures, hot fluid temperature and cold fluid temperature. Now, if we were to look at the temperatures, what I've made use of here is our understanding that the driving force for heat transfer is the temperature difference rather than the temperature itself, and therefore it's perfectly all right to define a dimensionless temperature, but here what I've defined is a dimensionless temperature difference. So to define a dimensionless temperature, one needs a characteristic temperature. Of course, just as you have a characteristic length, you take the absolute length and divide by the characteristic length, you get a dimensionless length. So if you take an absolute temperature, divide by a characteristic temperature, you will get a dimensionless temperature. But I have defined a dimensionless temperature difference here. Therefore, I need a characteristic temperature difference, which should go in the denominator. And I also need a characteristic temperature with respect to which I will subtract my absolute temperature, right? So I'll take the absolute temperature, subtract the characteristic temperature, and then do the same thing to get the characteristic temperature difference, in the denominator with respect to some other temperature. So therefore, this is the idea that is being utilized. So so theta c is the dimensionless temperature difference, and this is a function of y and tau. And this is basically defined as Tc, which is a cold fluid temperature at any z, any position z, any position time, any time t, minus the characteristic temperature is chosen as the inlet temperature of the cold fluid. In both cases, it has to be consistent in both cases. And then the characteristic temperature difference is considered to be the difference between the inlet temperatures of the hot fluid and the cold fluid. So taking this structure, dimensionless temperature differences are defined. Now, why this particular choice? What if some other choice is made? It is possible. It's perfectly fine to make other choices. The ultimate physics will be the same. That cannot change. However, there would be some conveniences or inconveniences making different choices. I hope to record a video at some point once we have done enough of these examples, such examples, discussing how to generally consider, if one doesn't know a priori what kind of a temperature characteristic temperature to choose, or characteristic temperature difference to choose, which one to go about, how to go about doing that, making that choice. I hope to record a video soon enough on that. So choosing this equation, so we get T is equal to L by Vc into tau. So dt is L by Vc into d tau. Similarly, z is L into y, so dz is L into dy, and so on and so forth. So the model equation, the equation that we derived from the shell energy balance, can be rendered dimensionless. And now this is in terms of dimensionless variables. This is the dimensionless temperature difference of the cold fluid with respect to a dimensionless time. This is the first derivative of dimensionless temperature difference of the cold fluid with respect to dimensionless position, right? So the structure of the equation looks quite similar to what we saw initially, as it should. Now, in this, you find that there is one term that shows up which is dimensionless. So I leave it to you as the listener as an exercise to show that this quantity indeed does not have any dimensions. All right. So this I am indicating as lambda. So lambda into theta h minus theta c. So the initial conditions that we started out with, at y equal to z equal to 0 is y equal to 0. For all time taus, all dimensionless times taus, right? The inlet temperature difference is basically, if you look at for the cold fluid, this is basically Tc in minus Tc in by Th in minus Tc in. Therefore, this becomes 0. Similarly, initially at all y's, everywhere along the length of the pipe at time tau equal to 0 or t equal to 0, initially your Tc is Tc in, and therefore your dimensionless temperature difference is 0 to start with. So these become your initial conditions. Now this is the first order differential equation, right? Partial differential equation, and this is typically called as the forcing function, and this is the homogeneous part of the equation. And here this lambda is a dimensionless group. This is typically indicated as number of transfer units. This captures the rate of heat transfer from hot to cold fluid to the rate of energy transport by convection of the cold fluid. So now we turn our attention to understanding what take-home messages we have from this scaling analysis, dimensionless, rendering the model equation dimensionless that we've done so far. So each process has multiple phenomena that influence the variables in the process. The process variables, if you don't know the unit variables, for instance, you want a certain outlet temperature and you want to know what should be the length of the derived heat exchanger, unit variables. So whichever be the relevant output variables of the process. For example, in the above problem, convection and advection, which is basically the heat transfer heat added, right, are significant phenomena that influence the heat transfer process and thereby the temperature of the cold fluid in the heat exchanger. The model equations as derived, the dimensional model equations, do not readily reveal the relative magnitude of the various phenomena. Knowing this would enable simplification and practical customization of a model, but the model equations do not say whether the rate of heat transfer is dominant, or the rate of convection is dominant, or both are of similar magnitudes, or what about the hot fluid side, what about the cold fluid side, and so on and so forth. So the equations are all there. I mean, we'll have to just simply solve them simultaneously. That is the only option pretty much left to understand how the system behavior is going to be. But if we go through this analysis of rendering the model equation dimensionless, the scaling analysis defines dimensionless groups which act as scales to the different phenomena, which have all then been normalized with respect to each other. So the lambda term that we saw in that equation is the single factor, the dimensionless group that is there, that is going to determine how things are going to change. The left hand side, we had partial derivative with respect to a dimensionless time, and then partial derivative with respect to dimensionless position. All right, all these are dimensionless, so everything varies between 0 to 1, 0 to 1, or 0 to a few numbers. In case of dimensionless time, you may have 1 t, 1 tau, 1 t bar, 2 t bar, 3 t bar, and so on. So a few values. And then the right hand side has had lambda into theta h minus theta c. Both theta h and theta c vary pretty much from 0 to some small values, magnitudes. So it is basically the lambda that determines whether if the lambda is very large, the right hand side dominates. The lambda is very small, the left hand side dominates. The left hand side is convection, the right hand side is heat transfer from the hot fluid to the cold fluid. So in one parameter, we basically, the magnitude of the dimensionless group determine which phenomena becomes significant, and that understanding can be obtained by looking at the magnitude of those dimensionless groups. And they also allow for us to design the processes very effectively. If you want to operate it under a certain type of operation, certain mode of operation, it's easy to go about doing that as well. So if we have derived a model for the cold side, now we go ahead for the hot side, but by similar arguments, the dimensionless energy balance for the hot fluid will be the same. Same kind of a structure will be seen. But now here the dimensionless temperatures in the initial conditions are 1, because if you recall, this theta is defined as T H in this particular case, right? TH minus TC in divided by TH in minus TC in. So the denominator has inlet temperature of the hot fluid minus inlet temperature of the cold fluid. So everywhere we are going to say initially the hot fluid was at its inlet temperature, and always at all times at the inlet, at the entrance to the heat exchanger, well, the hot fluid is at the inlet temperature. This corresponds to parallel or co-current flow. If this were counter current flow, then this condition would be at y is equal to Y is equal to 1 or Z is equal to L, because the hot fluid would enter at the opposite end. So that is how this condition changes between co-current and counter current fluid. Otherwise, the model equations are the same, right? So looking at this equation, this lambda, which is UAL by MCP V. All right. So the UAL, the numerator talks about it gives a measurement of the rate of heat transfer from the hot to cold fluid, and the denominator basically is a measure of MCPV, and that is the convection. So which dominates? So if the UAL term, the numerator term, dominates, then basically this temperature difference is going to play a major role, which basically means that there will be a significant change in the temperature of whether it is the hot fluid or the cold fluid, whichever you are looking at, along the length of the heat exchanger as well as with respect to time. Now, on the other hand, if the lambda is very, very small, then this can be fairly small and could be neglected, and then there is not a significant change in with respect to the temperature of the hot fluid or cold fluid, either equation, with respect to position or time. So this one parameter can reveal the physics. That is the idea. So to obtain the exact temperature profile in the exchanger, both the equations will have to be solved simultaneously. They are coupled equations. They are thankfully linear. This luxury is not afforded in most cases. They are non-homogeneous because they have their forcing functions. They are first order partial differential equation. So a simpler case, a model case arises when a hot saturated steam condenses on the outer wall of the inner pipe, meaning the inner pipes of annular region, right? At the surface of that outer wall of the inner pipe, saturated steam condenses into saturated water, and we consider steady state. So in such situation, the temperature of the hot stream, the hot fluid is constant. So TH is constant, theta H is also constant. At steady state, then the cold fluid equation then can be the time derivative can be neglected, and the partial differential equation can be replaced by the ordinary derivative. Partial derivative can be replaced by ordinary derivative, and this then gives very clear indication of how the variation is going to be. This equation is of the form dy by dx plus py is equal to q, where this is the forcing function. So this is basically going to give you the basic picture of how the variation is going to be. Like, this is the homogeneous part. This will give an exponential solution with respect to y, and that forcing function will merely alter the nature of the solution while keeping the exponential form the same. And lambda is basically, again, depending on whether the rate of heat transfer dominates or the rate of convection dominates, the the extent of variation in the cold fluid temperature will be different. If lambda is very, very small, then basically there is hardly any variation. Basically, taking this to the other side, d theta c dy is hardly any there is any change with respect to y of theta c, so the temperature will be almost constant. Whereas if lambda is very large, then there will be a significant variation in the temperature of the cold fluid with respect to position. So this equation, the solution for this equation is a response that one is familiar with in process control as first order response. Here, of course, this is with respect to position, not with respect to time. So this kind of a behavior results for different values of lambda, right? So here, it is clear why you are looking at lambda as a number of transfer units. So lambda equal to 1, 2, 3, 4, and so on and so forth. Theta c, which is the cold fluid temperature, gradually approaches theta h, which is constant, right? So after about 3 or 4, lambdas, basically after 4 lambdas, your theta c is 98% of theta h. So this is the idea. So this sort of gives a simple enough solution for a specific case, but the model itself is fairly powerful and general, right? So with this, we come to the end of the first part of this lecture. So where we have considered a one-dimensional model of a double pipe heat exchanger, purely thermal model, assuming that the velocity is constant, and we have then rendered the model equation dimensionless, and then we have considered a specific case where we have saturated steam condensing on the outer side, and thereby the hot fluid temperature is constant, and we have been able to obtain analytical solution for that particular situation. And the take-home message is that the governing sort of parameter, that sort of decides how the behavior is the relative magnitude of rates of two competing phenomena, one being heat transfer, the other being bulk convection of the material along with its energy. So this ratio is captured by the dimensionless group lambda, and that lambda turns out to be number of transfer units. Thank you for listening to this lecture. If you have any questions, you may please post them on the YouTube channel, or if you are one of my students in one of my classes, you can reach me otherwise, or you also know my email ID, which is available in my website, a link for which is provided in the YouTube channel. Please feel free to contact me. Thank you very much once again for listening to this lecture, and I hope you have a wonderful day. Bye.